The inflationary cosmology bit is probably the most widely accepted theory at the moment for how the universe got to be the way it is. And it does lend itself to this idea that there may be a multiverse. And it may be that in each different pocket universe, if you like, you can have different physical constants. So most of them wouldn't allow life to exist, but some of them would. So our universe looks very fine-tuned if you look at it, in a sense. It looks like the laws of nature were very slightly different. You wouldn't get carbon, for example, produced in stars in large quantities, which you need in order to, and when the stars die, the carbon and the oxygen come out and they relapse into another generation of stars and solar systems, and that's how you get the heavy elements that make up our bodies. And you either try and find an explanation for why the laws of nature are the way they are, or you go to one of these multiverse theories and say, well, actually every possibility occurs in nature, and then we shouldn't be surprised that we live in a universe that seems fine-tuned for life, seems perfect for us to exist in, because every possible combination of the laws of nature exists somewhere on what's called inflationary cosmology, and it is cool and interesting, actually.
Yeah, it's beyond that. The idea of something being infinite, and not just infinite, but infinite numbers of these infinite things. So this idea of computer simulation, the world we live in, the universe we live in, the idea being that one day, if human beings continue to increase our technological abilities, one day we're talking about this magic leap, and we're talking about the goggles that allow you to see a virtual world. We're going to, if we don't blow ourselves up or get hit by an asteroid, we're going to come up with something that is indistinguishable from the reality that we see right now. And when people start examining the nature of the universe, and they start looking at the fractal nature of things, and looking at, like what you were saying, that if you were going to be some omnipotent deity that creates the universe, you'd probably do something like this, like every single combination, and throw them out there. So when we discover, like it was a guy who spoke to Neil deGrasse Tyson about string theory, and that they found in string theory this computer code that was created by humans in like the 1930s. They figured this out, and that this actually exists in these codes in string theory. And his idea was that somehow or another proves that there is some evidence to support that life, the reality that we see right now, is a simulation. Or it could be that, which way more likely, that you're just discovering some sort of code that the entire universe is based on. That when you look at things being fractal, and you look at the idea of there being not just infinite expansion, but infinite contraction, and that there is no smallest point. There's just smaller than we can measure. But when we talk about subatomic particles, and we talk about things being like atoms being mostly air, and then you go deeper and deeper, and you don't know what the fuck is going on, and particles are blinking in and out of existence and existing at the same time, both moving and still. But could it be that you just got to keep getting, we just can't see it?
Well, the answer is, we sort of do know what the fuck's going on at some level with subatomic particles.
Right.
If you look to the LHC, which is the Large Hadron Collider, which is the place where we generate the highest energies, so it's the biggest microscope in the world in that sense. We have an extremely good understanding of the laws of physics at that level. Up to and including the discovery of the Higgs particle. There is a particle there that we've discovered, and it has all the right properties to be the predicted standard model Higgs particle.
Please explain what that means.
So the Higgs particle, it was predicted back in the 60s by Peter Higgs and others, hence its name. And it's the idea is basically that early on in the expansion history of the universe, so let's say less than a billionth of a second after the Big Bang, as the universe cooled, it went through something condensed out into empty space. So people call it a phase transit out. So empty space isn't empty. It's full of Higgs particles, if you like, or a Higgs field. Wow. So this means this space. Now, it's not just space between the galaxies, it's in this room. That every square meter of this room is full of the Higgs field. And our fundamental particles, the electrons, let's say, in our bodies, interact with that Higgs field. And in that process, they acquire mass. So it's the mass generation mechanism. It's why some particles are massive, like electrons and quarks, and some things like photons are not massive. They're massless, and they travel through the universe at the speed of light. So that's the theory. Now, that was suggested and built mathematically, essentially. There was very little evidence for it at the time, back in the 60s. But over the years, the theory, called the Standard Model of particle physics, passed all experimental tests. So we got to the point where we thought, right, okay, we will build a machine that will either disprove or prove that theory, and the LHC is such a machine. If that theory is correct, which it now seems to be, the prediction is you must find the Higgs particle at the LHC, or some kind of Higgs particle. And indeed, we found it. As far as we can tell. So that means that we found a new particle. It has the right mass as predicted in the window that was predicted by the theory. It behaves in every way like the theory predicts. But that's a remarkable thing to think about it, because it's Wigner, a great physicist, wrote an essay back in the 60s, I think, called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And by the unreasonable effectiveness is demonstrated by this discovery, because it really is a mathematical prediction. It's like we think there's a new fundamental particle that does the job of giving mass to the other particles, and this is how it does it, and this is how it behaves, and this is what it will look like, and this is what it will do. And then 50 years later, you build the biggest machine ever built, and you find it. You find this thing that this guy, Peter Higgs, working with many other people, predicted to exist 50 years ago because he did some surprise. So it's a tremendous testament to the power of human reasoning, I think. And it means that we understand physics. It means that that's one of the important things about it. It means that our understanding of fundamental physics is not horribly wrong at the moment. It's good enough to predict something like this. The day that the discovery was announced, and a journalist went up to him afterwards, and just what I've said, this is what happened. This machine did it. He found this thing, and said, "How do you feel, Professor Higgs?" And he said, "It's very nice to be right sometimes." That's what he said. Brilliant. Understand.
The Large Hadron Collider also figured out or proved quark gluon plasma.
Yeah, so that's a later
explain that
in the universe, in the history of the universe. So way after the Higgs mechanism kicks in, you have a period when it's still too hot for protons and neutrons. So you get this thing just before it gets cold enough to condense into protons. Is this about a millionth of a second after the Big Bang? So quite a long time.
Quite a long time.
This is a lot has happened from that point.
Relatively speaking.
So we can do that as well and see how that phase of the universe behaved.
And that stuff is supposed to be just immeasurably heavy, right?
Oh, the atomic nuclei.
Yeah.
I mean, if you look at, so an astrophysical example would be a neutron star, which is basically a big nucleus, nuclear dense material, the end point of a collapsed star when it's run out of fuel. If it's not too big, if it's too big, it'll turn into a black hole. So a neutron star would be 1.5 times the mass of the sun, let's say, something like that. But it would be a radius of 10 miles. So it would easily fit in the LA metropolitan area, right? But it would have the mass of the sun or greater. So that's an atomic nucleus density. That's how you can imagine it. Something as massive as the sun compressed into something 10 miles across. And we see these things all over the universe. Neutron stars are fascinating things.
Someone online was explaining it. Some physicist was explaining that if you had this quark gluon plasma and it was the size of a sugar cube, it was some ungodly amount of weight.
Yeah,
like you couldn't even imagine it.
Mount Everest, that kind of.
It would be like Mount Everest.
Yeah, I can't quite.
Fucking sugar
but
cube.
It's something enormous. It's like
you broke my brain.
Well, if you think about it, all our mass is in. You alluded to it earlier. All our mass is in the nuclei, and if you got all our atomic nuclei, mining your nuclei and stuff them together into that density, it would be a grain of sand or something less size. So you could. I mean, you think about the universe. I mean, the modern theories of the Big Bang, as we talked about earlier, these inflationary cosmology theories, they suggest that the entire observable universe, which has now got 350 billion galaxies in it, was at some point the size of a baseball or less. So we imagine, or we speak of in modern physics, we have theories that address the time when the entire observable universe was something
that you could hold.
So you've got enough energy in there to make 350 billion galaxies, each with 200 billion stars. And it's that's the physics we're doing at LHC. Basically, we're trying to explore the laws of nature and find the laws of nature will describe the universe when it was that hot and things like that. And so we understand that very well. So the challenge now is to get back beyond that, and that's where string theory attempts to live, which you mentioned earlier. String theory, we don't know if it's right. We have no evidence to that it's an approach to trying to describe the universe before those times when our current law